Welcome. Today we're going to be taking a look at the notes worksheet entitled Operations with Complex Numbers in Polar Form, Day 2. And so it is definitely time to get your game face on here. There is some pretty heavy, complicated number theory that we're going to be taking a look at. I will, of course, try to walk you through it as best as I know how. So we'll do some review from the previous lesson and then kind of build a nice foundation here with what's called Moivre's Theorem. And we're going to be doing powers with complex numbers and roots of complex numbers. So some different operations. And well, let's see what's ahead of us here. Let's start it out. Everybody at the top of your paper, it looks like I have an A through E just to get us thinking in the right direction here. First and foremost, it says what is the polar form of a complex number? So if you remember, what we have at this stage is two representations of a complex number. What's called rectangular form or standard form, a plus bi, and then the polar form is that r cis theta. So I'm going to do my z, you sort of see that as representing the complex number here, and so this would be r cosine theta plus I sine theta. Okay, so that is our polar form, and in order to be successful today with the two operations we're going to see, powers and roots, we have to be able to convert from rectangular form to polar form. So we have to go from A and B to our R and our theta. We have to find those pieces. And so if you remember correctly, again, this is math now we've been doing for a little bit of time here, so there we go. R is just equal to square root of a squared plus b squared. So remember, the horizontal squared and the vertical squared equal kind of the direct squared, the radius squared. So that's how we get our R. And then this is sort of how we get our theta. And there's a reason this blank is a little longer here. So just inverse tangent of the vertical over horizontal. That's always the ratio for tangent. And here's how I'm going to write it. Just if A is positive, pretty much you can leave it as is there. And then just don't forget, of course, inverse tangent of B over A. But don't forget adding that 180 or pi. So we'll probably go degrees today, really, for the most part. I think it'll make our lives a little easier with some of this stuff. But if A is negative, you do have to add 180 in order to get it in the proper spot. So those are the two connections that we're going to be doing, and as I mentioned, really the first step in what will be a pretty difficult process is being able to go from rectangular form to polar form. So definitely need you to be able to pull that off. And then I guess this is just a review from yesterday's lesson. C and D kind of go together here. So it says, how would you multiply two complex numbers that are in polar form? And I'll keep it nice and simple for us. We were a little more formal yesterday, but multiply the r's, I'm going to put a little s there, and add the thetas. There you go. Multiply the r's and add the thetas. And again, we took a look at some nice patterns yesterday, and it worked out quite well for us. If we're going to divide divide two complex numbers that are in polar form, we divide the r's and subtract the thetas. All right, so that was just the review from yesterday. 4 operations that we're looking at here with the complex numbers in polar form. So multiplying complex numbers, dividing complex numbers, powers of a complex number, and roots of a complex number. So I believe, if I remember correctly, we ended yesterday's lesson talking about Moivre's theorem based on raising a complex number to a power. And this is what we came up with. So in order to pull this off, just like here, everybody, when we go ahead and do our operation, we have to change r somehow to create a new r, and we have to change theta somehow to get a new theta. And so it worked out quite nicely, if I remember correctly. We change r by raising r to whatever power. That's easy enough. And then we change theta by the factor of what we're raising it to. So if we're raising it to the 5th power, this would be 5 theta. If we're raising it to the 12th power, 12 theta. So raising it, well, I should say we're changing the theta by a factor as opposed to anything else. So in this case, let's go ahead and put that sine of n theta. Okay, perfect. All right, so that's, I think, where we'll start. The raising powers is definitely the easier of the two, so we might as well get a little confidence builder going here, hopefully, and do our example one. So I have a variety of answer blanks down here for us just to kind of solidify some things as we go through the process. And I guess I would argue the first thing we're going to get is we're even going to forget the fact that it's raised to the 8th power. What we need to do is change the complex number into polar form. So everyone, on your paper, you can kind of see this piece. This is our complex number in rectangular form. Everybody, before we can raise this son of a gun to the 8th power, we've got to change that to the r cis theta. So let's go get them. So first order of business, here's basically what I'm thinking. We have to go ahead and get z. So our z right now is 1 plus I. And so in order to pull this off here, I'm going to have to figure out what that is in polar form. And so I'm just going to try to find some room here to do a little work. I'm going to go right over here as I'm kind of looking at it. And I'm trying to be visual with it. I'm a very visual person with a lot of this math that we're looking at. And 1 plus I, everybody, would be right up here, give or take, in the first quadrant. It has an r, and it has a theta, of course. So let's get those two pieces. I'm going to work over here for right now. And r is equal to, remember, by the way, guys, this is a 1 plus 1i. So 1 plus 1i. So the a value is 1. And please don't forget, I have seen students struggle with that piece. The b value is also 1. It is the coefficient in front of the imaginary unit there. Okay, so 1 squared and 1 squared should give us square root of 2. Okay, so that's pretty good. That's a good start. Everybody should be able to come up with an r value based on a and b. Okay, now everybody, we need a theta. So I do my theta, inverse tangent of, in this case, 1 over 1. No need to add 180 degrees. And by the way, just kind of thinking out loud with this, you know the inverse tangent of 1. That is something that we looked at certainly in previous units. But I'm going to go ahead and get my calculator up. I'm going to go degree mode. I would encourage you to do the same. And I'll just try to be as formal about this as possible, but basically what I want to do is inverse tangent of 1 divided by 1. And so I do my inverse tangent of 1 divided by 1, and I end up getting 45 degrees. And if you look at my drawing right here, that should make perfect sense. So theta is 45 degrees. So as I mentioned, before we can even talk about raising this complex number to such a large power, in this case the 8th power, we need to know what that complex number is in polar form. And so now everybody, I have my r, and it's cosine 45 degrees plus I sine 45 degrees. Hoping everyone's okay with that piece. And as I mentioned, that is the first step. That's what we did when we did one of the notes worksheets before. I believe it was called the complex plane. We converted from one form to the other and must be able to pull that off. Okay, so that is 1 plus I right there. Exactly the same number, just a different way to represent it. Okay, everyone. Now what we're going to do is take our complex number and raise it to the 8th power. Now don't write this on your paper. I'm just kind of thinking out loud for a sec here. Remember what 1 plus I to the 8th actually means. If we were really to kind of do this the long way, so to speak, that would be 1 plus I times 1 plus I. We would be foiling, then we'd foil again, and foil again, and foil again, all the way 8 times there. That would be the really super long way to do it. Unpleasant at best. Terrible, to say the least. There's another way to maybe do this using what is called the Binomial Theorem, but still, not easy. Not easy. Takes time to develop, all that stuff. So de Moivre and his little theorem here, it just represents an easier, a more simplistic way, and simplistic is a relative term, a more simplistic way to go ahead and raise a complex number to a particular power. It works better when it's in the polar form. Because now, everybody, I'm going to have to come over here a little bit just to make sure I have enough room. Now I'm going to take my complex number and I'm going to raise it to the particular power, in this case to the 8th. So everyone, if you would, let's go for it. It basically says take your r and raise it to that power. Okay? And then take your theta and change it by a factor of 8 in this case. So instead of, don't do 45 to the 8th, that doesn't sound right. It would be 8 times 45. And as I said, really not too bad. We change our r and we change our theta. This would be in degrees, this would be in degrees. Perfect. Okay. So that's pretty much it. Now I just have to clean it up a little bit and see what unfolds. But I'm going to do root 2 to the 8th. And then, guys, I'm just going to do 8 times 45. Not bad at all. Not bad. So let's go ahead and bring my calculator up here. And you guys do the same. Can everyone do square root of 2? Close that off if you would. And raise it to the 8th. And you might be able to kind of work this out in your head. But root 2 times root 2, etc., etc., 8 times over, really should just be 2 to the 4th. And there it is. There's your 16. Okay, so our new r value is definitely 16. There's our root 2 raised to the 8th. And now, everyone, what I'm going to do is 8 times 45. That one I don't need my calculator for. How does 360 sound to everybody? Okay. And as a matter of fact, we just did it. We just raised that number to the 8th power. It just happens to be expressed in polar form. So that's what I'm going to make sure we write right in here. But in essence, guys, we did our job. Now, the only thing I would argue is we did originally have it in rectangular form. It was 1 plus I to the 8th. So I would like to keep it in rectangular form as a result. So even though we kind of did a conversion to get it polar, let's go on back and let's convert it in order to get rectangular on this. And so here's what I'm thinking. Let's just do 16 and just think of your unit circle. If you can't pull this off, you can grab a calculator to assist you. But you should know that the cosine of 360 degrees is exactly 1. So think about where that is on the unit circle part, right here, starting it out, and cosine value is definitely 1. And then it looks like I have an I, and then how about 0 right there. Bring in the arrows, distribute. 16 times 1 is 16. 16 times 0i is 0. And so as a matter of fact, if I did 1 plus I times 1 plus I times 1 plus I, etc., etc., etc. there, 8 times over, that would be my answer. Okay, so again, number theory, complicated number theory here, working with complex numbers and raising them really to any power. De Moivre's theorem just is a nice concrete way to pull it off. All right, so guys, that was letter A. Obviously, what we want to do is reinforce. So let's go ahead and do letter B. Same thing. It's a 3-step process, and I like the way the answer blanks are laid out there for us. So first order of business is to convert. So everyone, I come over here and just try to be as clear as possible as to how this is going to play out. So -1 plus root 3i. So on the complex plane, it would be 1 to the left, root 3 up. Yeah, something like that, give or take. Doesn't have to be perfect. And I would be looking for my r value and my theta. All right, guys, I'm going to get it moving along here. Be with me on it. So I have -1 squared and then square root of 3 squared. Hopefully you can kind of see that piece. All right, so -1 squared plus square root of 3 squared. When I do this, by the way, everyone, I get a 1 plus 3 underneath the root. 1 plus 3 definitely would be 4. And square root of 4, I'm coming out with just an integer of 2. All right, so our new r value, well, I should say, our r value for this complex number is going to be 2. Now the theta, everybody, let's do a little inverse tangent. So inverse tangent, root 3 over -1. Everybody think about it for just a sec before we do it. What do I need to add on top of this? Everyone take a peek. The horizontal part is negative, so I must, by our rule of thumb, add the $1.80 on it. So let's go ahead and see what happens here. And again, I think to some degree you already know this, but if not, no big deal. So let's see, inverse tangent. I'm going to do that square root of 3. Remember, do the same, everybody. Make sure you're able to kind of execute with me. Plus the 1. I'm going to close that off. And then how about we add the 180 degrees on top of that for a good measure. And it brings us into the second quadrant. So 120 is our angle. And by the way, when we did an inverse tangent of that negative root 3, it actually gave us negative 60 degrees. It would give us something, it would give us the angle down here. Obviously, we wanted to get to quadrant 2, so that's why I add that 180. And notice, just even based on my little drawing there, you could see that's a pretty good, reasonable answer. Okay, so we have z in its other form. So it's 2, and let's see, I have cosine 120, and then I sine 120. That looks absolutely outstanding. I'm going to write it down here too. Feel free to do that or not do that. It's your call. But I sort of think it's a good 3-step process there. Might as well keep track of our 3 steps. Okay. Now that we have it in its polar form, we'll let Moivre take over. And based on that theorem, what we're going to do is take that complex number and very simply raise it to the 12th. Raising it to the 12th in standard form is just no picnic whatsoever. But raising it to the 12th power in polar form, not too bad. Because all I have to do is change my r by raising it to the 12th and change my theta by multiplying by 12. And let's see, I sine 12 times the 120. There we go. Let's clean it up and sort of get everything taken care of here and move on to the next piece. Let's see, 2 to the 12th, I've got this one. I'm seeing it as 4,096, if I've got that right there. So I might want to grab a calculator and verify that piece, but I'm going with a 4096 on that. And then this one here, let's go cosine, should be 1440, and then I sine 1440. Not ideal by any means. Several rotations in order to get this particular angle measure, but I think it'll work out in the end. And so it looks like we have picked something basically like this at this stage. So 4,096 cosine of 1440, and then I sine 1440. All right. Good. Now the only dilemma is sort of seeing this 1440. And just to help us along a little bit here, I'm going to go ahead and sort of sketch it out. And you don't have to do this on your paper, just kind of thinking out loud with this. I'm sort of thinking of my rotations around. If I start here, everybody, once around would be 360. Twice around would be 720. 3 times around would be 1080. And as a matter of fact, if I go a 4th time around, 1080 and 360 make 1440. So as a matter of fact, and if this doesn't work for you, you are more than welcome to grab a calculator and just type in cosine of 1440 degrees. But the bottom line here is the nature of our trig functions being periodic. I think 1440 degrees just puts you back right at that spot. And if I'm at this spot right here, I should be able to know the cosine value and the sine value. So that's what I'm thinking for our last piece. And so I'm getting a 4,096. Cosine of 1440 should be 1. I hope everyone is cool with that piece right there. And then same deal. And by the way, it's coincidence the way this is working out. Similar to the last one, as you can see. But bring in the arrows, distribute, and I'm getting just back to the real number system. So -1 plus root 3 times I, all raised to the 12th, is 4,096. Excellent. So as you can see, some pretty heavy-duty math there. And that is just the tip of the iceberg for today's lesson. Okay, let's go for it. Let's move on to the next. So, powers, that's done. Now it's time to get on to the last operation, the roots. So this is just the 2, 3, and 4 that you see on the screen at this stage, just really very simply an Algebra 2 review. In fact, it comes from something called the Fundamental Theorem of Algebra. So it says, how many roots or solutions does each equation have? So if you remember solving equations like this, these polynomial equations, or treating them as functions and finding the zeros of the functions, well, very simply, how many different solutions would there be to this particular equation right here? Well, if you look at the degree of the polynomial, everybody, which happens to be 6, that is our indicator right there. And if you remember correctly, very simply, a polynomial equation of degree 6 has exactly 6 solutions to it. It's what's called, again, the Fundamental Theorem of Algebra. So a quartic equation, like this one right here, has 4 solutions to it. Now, the composition of those solutions varies, and we don't need to go into that at this stage. But essentially, this one right here, x to the 8th plus 1 equals 0, has 8 solutions to it. And so what we're going to start to do, especially letter A, by the way, as that is going to be one of our examples, we're going to be able to sort of work with that concept of finding the roots of a particular value. Okay, so let's move forward with this. Example 3. Perform the operation 2 to the 3rd and use the idea of roots to rewrite the problem. Okay, I seem to recall why I put this on here is just to really make the connection between powers and roots. So we don't have to overthink this at all. Here's what I'll just ask you to do, and then we'll go right on to the next one. So 2 to the 3rd is equal to 8. And what that means in terms of powers and roots, I can rewrite this equation using its opposite operation. We've done that so many times before. Essentially what that means is that 2 is a cube root of 8. So those two things mean the same thing, just written in their opposite operation. So if 2 to the 3rd is 8, then 2 is a cube root of 8. I'm hoping everyone agrees with that statement, and that will allow us to sort of take the next conceptual step. Now, one thing to note before we go ahead and do the next one on your paper there, what this is basically telling us, and the Fundamental Theorem of Algebra is telling us, and de Moivre will be telling us, is that 8 has, as a matter of fact, 3 different cube roots. So one of the cube roots of 8 is 2, but there are actually 2 other cube roots of 8. And we would use de Moivre's theorem to kind of pull that off. Okay, so let's do one more, again, just to get that idea taken care of. And keep paying attention with that. And so it says use the idea of roots to rewrite your answer from example 1a. If you remember our example from 1a, we got this. So this is what you're going to write on your paper, everybody. We got 1 plus I to the 8th. We got that equals 16. Okay, by definition, we raise this to the 8th power, and it equals 16. So what I'm asking for is just to put this together in the context of a root. What that would mean, everybody, I'm hoping, again, you would agree with this statement, that 1 plus I is an 8th root of 16. Everyone okay with that premise? And let's take it half a step further before we get into de Moivre's theorem. 1 plus I is one of the 8th roots of 16. I'll say that again. 1 plus I is one of the 8th roots of 16. So this number right here has 8 8th roots of it. And our job would be to find them. So when we talk about complex roots, if I'm talking about square roots, every number has 2 square roots, 3 cube roots, 4 fourth roots, 5 fifth roots, etc., etc. All right, well, let's go get the big boy here. So, as it says, complex roots, de Moivre's theorem. Now this one's going to look a little more complicated, but we'll go through, got some strategies, and we'll do a couple examples to put it together. So it says, for a positive integer n, the complex number, here it is written in polar form, everybody, has exactly n distinct roots given by, and here's what we're going to play. Now I'm going to introduce a k value just for the time being, and we'll go through exactly what k is. And we'll try to shortcut k a little bit, by the way. So to find roots, just like finding powers, we have to change our r value of the complex number, and we have to change our theta of the complex number. And so that's what we're going to do. And again, logic takes over. If you remember when we did powers, we raised r to a power. Here, guys, we take what is called the principal root of our r to get our new one. So principal root of r, and then this is where it gets a little chaotic. So it's cosine, and here's how we change theta, everybody. We do 360 times this k, which I'll bring up. But notice, this shouldn't be a shocker. If you remember when we did powers, we multiplied theta and n together. In this case, everybody, we divide. Theta divided by n instead of theta times n. So again, that shouldn't come as a great shock that you see a theta divided by n here for the roots. Now this 360k is something we'll have to navigate through. Okay, and then I sine, and then let's do the same thing, everyone. So 360k, and then over n. And just off to the side, here's what I'm going to do. And as I said, we're going to try to work our way around it. We've seen k before. K basically is an integer. In this case, we're going to let it just take on values here. We're going to start it at 0. Then we're going to let it take on 1 and 2 and 3, all the way up until when we're done. Now, as I said, I'll discuss more of that as we go through the process, but I think I'll need to be a little more concrete with that because at this stage, there's no real basis for us to do it. But everybody, that is your, let me just make sure I've got one more parenthesis there. There we go. So that is our formula for finding the nth roots of a complex numbers. Okay. So here's some strategies, and we can kind of take them for what they're worth. But the first order of business, as you see, is we have to write our number in polar form. So whatever z is, we're going to go polar on it. Moivre's theorem deals with the fact that it has to be in polar form. Now, once it's in polar form, we're going to use the formula above, and we're going to put in n, we're going to put in r, we're going to put in theta. K we're going to leave blank for just a little bit. And then we're going to start working with k. Again, k is sort of our curveball right here, and we'll deal with that. It says beginning with 0 until you've found all the roots. Okay, that doesn't mean much to you at this stage because, as I said, there's no concrete problem with it at this point. So it's time to go ahead and do one. And nothing like starting out with a big one right here. So, example 5. Here we go. It says, find all the 6th roots of 1. And so, just very quick conceptually, and then we will get the ball rolling with this. How many different 6th roots of 1 are there? Well, very simply, there are 6 6th roots of 1. And what this means, what I'm looking for, if you sort of look at what we developed at the top of your page, we're looking for all the numbers where if I raised it to the 6th power, it would give me 1. Is everyone okay with that idea? When I'm asking for the 6th roots, what I'm asking for, and don't write this on your paper, is something to the 6th has to be equal to 1. And there are 6 different values where that happens. Is everyone okay with that premise? And that's sort of what the fundamental theorem of algebra shows us, and that's what Moivre sort of, it takes over essentially. That there are 6 different numbers that if I raise them to the 6th power, I would get 1. So you could think of a couple just off the top of your head, right? Think of a number that if you raised it to the 6th, you'll get 1. I can think of 2 just off the top of my head. I don't want to give anything away. Those will be part of our solution set. But I can think of 2, which means there are going to be 4 others, which I can't think of. So let's start it out. Everybody, be visual. Find the number 1 on the complex plane. So your first step is to take the number 1 and convert it to polar form. Now it seems kind of silly, right? Just the number 1, something you've seen now for years and years and years and you've worked on, but never, never with this level of difficulty. So the number 1 would be right here on the complex plane, and that would be theoretically a real part of 1 and an imaginary part of 0. So 1 plus 0i. That's it. That's the number 1. Rectangular form of a complex number. Now, everyone, what I need us to do is find r and find theta. So here's how it's going to play out, everyone. R is equal to, let's go for it, 1 squared and 0 squared. Again, this should now be, at this stage, just about automatic. Here's your A and your B. And let's go ahead and get our r value. I'm hoping you see that it's square root of 1, which is 1. And by the way, take a look at that. You know, here it is, the number 1. How far is it away from the origin? It's 1 unit. R is 1. Theta, everybody. Inverse tangent. How about we go 0 over 1? And inverse tangent of 0. If it's okay with you, I'm going to go ahead and get what the calculator would give me here. And we know this inverse tangent of 0 happens to be 0. Okay, so our first step was to go ahead and get our complex number, and it happens to be 1 cosine of 0 degrees and I sine 0 degrees. So I will stop right there for a second and just make sure that makes sense. Write the number 1 in polar form. I know it seems kind of crazy to do. Obviously, the number 1 is quite a bit simpler than this, but this actually is the number 1. 1 cosine 0 plus I sine 0. Okay. Now we let Moivre take over. So here's how it's going to work. Give me a z with a sub k there for me. And what we're going to do is change our r and change our theta. So what we do on r is take what's called the principal root of r, the principal root of 1. So the 6th root of 1 if we were to do it on our calculator. And by the way, the 6th root of 1 should be 1. Okay, now cosine, we're going to take 0. We're going to keep this 360k in, and we're going to divide it by, what do you all think here? So what is our n? And in this case, since we want the 6th roots, n is 6. Okay, so divide by n, divide by 6. In powers, we multiplied by n. Here we take our theta and divide by n. Okay, and then I sine, same deal, everyone. I'll go parentheses on this too. 0, 360k, all over 6. Okay, and that's pretty good. It's a great first step. Well, it doesn't seem like it's a first step, does it? But that's all right. So, a couple things to get it going. Number 1 is this is going to be 1 right here. Now what we're going to do is let k start taking on particular values. And as I said, I'll try to show you what I would consider a shortcut that will allow us to go ahead and get our angles in a little more simple fashion. So I'm going to sort of go like this, everybody. I'm going to go to the other side of my board and see what happens here. But ultimately, hopefully I left you enough room. What we're going to now do is let k take over. Typically what you do is you start at 0, because 0 is the easiest number to go ahead and put in for k. And so what we're going to do now, everybody, is this. The principal 6th root of 1, if I had to do the 6th root of 1 on the calculator, you would get 1. So our r is 1. Now everyone, if k is 0, watch the math here. If k is 0, I'm hoping you would all agree that this just goes away, because 0 times 360 is 0. And then I would get plus 0 on top, and 0 divided by 6 is still 0. So as a matter of fact, our first answer in polar form is that. Now put a little equals on the back there, because what we're going to do is come up with the rectangular version momentarily. Okay, now the concept would be to let k take on the next number, and the next, and the next, and the next, until we get all 6 answers. So you could see in this case, I'm hoping, I started with 0, then I'm going to put in 1, then I'm going to put in 2, then 3, then 4, then 5. I know there are going to be 6 answers, so it seems like it's going to be in terms of k, 0 through 5. And that's how it's going to play out. So watch what happens. Keep with me. And as you go through this, always pause, put a question mark by something, and then ask if something comes up. Okay, so now I'm going to let k be equal to 1. So now k is 1. So 1 times 360 is 360. 360 plus 0 is still 360. And now let's divide by our n, divide by our 6. And 360 divided by 6, everybody, is 60. So as a matter of fact, our new angle on our second level right here would be 60 degrees. Put a little equals on the back, as in about 2 minutes, we're going to go ahead and convert that over. Now here's the thing. Theoretically, I would be doing this. So I got 1 answer, 2, 3, 4, 5, and I know there are going to be 6 answers, so I would have 6 answers run just across like that. 0 through 5 in essence. So theoretically, I would go ahead and put 2 in for k, and I would do 2 times this plus this divided by 6. What I'm going to try to do is give you a shortcut on this in order for us not to have to put in all these k values. And here's what I'm thinking. Did you see that our angle went up by 60 degrees? 0 to 60? Well, very simply, that change stays constant as we go through the process here. And so as a result, all I have to do, and sorry, I missed the 1 there, all I have to do is add another 60 degrees. That's my next angle. Now you'll find ways to even shortcut this probably a little further, but I know that my angle is just going to keep going up by 60 degrees. Oops. And so now, everyone, we can let it run a little bit, and let's get some answers. Okay, and then this one here, if I add another 60 degrees, and then if I add another 60 degrees, and then we'll pause for a moment, let you guys write all this in, of course. But as a matter of fact, those are my 6 answers. If I took each of these numbers and raised it to the 6th power, I would get 1. What I would love to see is this in rectangular form. But one thing at a time. So we had to find the first and the second. I don't think there are too many ways around that. I mean, I can think of a couple, but I would ask you to get the first and get the second. Whatever that change is, that stays constant. There's actually a nice visual look at Moivre's theorem. If you get an opportunity to look through your textbook a little bit, you might just see, I'm not sure if it put it in there, but a nice visual representation of these 6 roots and that angle kind of changing. But regardless, that seems to be what our answers would be. Now here's the idea. What if I'm like, wow, I just keep going and going and going. What if I let k just keep going here? What if I didn't know to stop at 5, basically? Well, guys, if I put in 6, like z and then a little 6 here, I would follow my pattern and I would add another 60 degrees. And don't write this on your paper, but you would, of course, get cosine of 360 degrees. Well, guys, what do you know about 360 degrees? Doesn't then have the same trig ratios as 0 degrees. And so, in essence, doesn't this just repeat the process? Because when I go ahead and get my answers here in rectangular form, wouldn't that be the exact same as doing this? And even still, what if I was like, all right, I'll keep adding another 60 degrees, so I go up to 420 degrees. Well, you know what? That would be the same answer as this. So in theory, it doesn't actually matter where you start, as long as you get in your cycle and get 6 different answers here. You get them. You get them. The easiest thing to do is start at 0, and that's why I did. But I could have started at 2 and done 6 problems. Okay. Hey guys, let's get our answers in rectangular, and we'll try one more. So you know this. Just think unit circle here. The good news is all I'm going to do is distribute a 1 in, so this is nice. So cosine of 0 is 1, and sine of 0 is 0. So as a matter of fact, one of the answers is 1. And do you remember I asked you to think of a couple numbers raised to the 6th that would give you 1? Well, we all knew this one, right? 1 to the 6th is 1. So you knew that was going to be one of the answers. Here's another number. If you raise it to the 6th, you would get 1. Cosine of 60 degrees, everybody, is 1/2. Sine of 60 degrees is root 3 over 2. So I know it sounds crazy, but if I take that number and raise it to the 6th, I would end up with just 1. Just do another one. Cosine of 120 is negative 1/2. Sine of 120 is positive root 3 over 2. Same deal, guys. Sorry for being redundant, but I think it helps. If I took this number and raise it to the 6th, it just gives me 1. Here's another one I think you would have figured out. Cosine of 180 degrees, everybody, is negative 1. And of course, what is negative 1 raised to the 6th? 1. And the other two right here, let's see, this one would be down in the 3rd quadrant, so negative 1/2 minus root 3 over 2 times I. And the last one down here, I'm getting a positive 1/2 minus root 3 over 2 times I. So the number 1 has 6 different 6th roots. 6 values that if I raise them to the 6th power, it's tough to spit all this out, you would get 1. And those are your 6 answers. Let's go ahead and, I don't know, try to box that up if possible here. Let's see. There we go. Not too shabby. Looking good. Awesome. All right, let's try one more. All right, seems pretty tame, right? Find the square roots of I. Now let's get a couple things out right away. How many square roots of I are there? There are 2 square roots of I. There are 3 cube roots of I. There are 4 fourth roots of I. That's the number theory that goes with this. And so in this case, I want the 2 square roots of I, meaning I want some number, whatever it may be, just thinking, so I've just put an X, where if I raise it to the 2nd power, if I square it, it would give me I. That's what I'm looking for. There are 2 different numbers that if I square it, I'll get I. Okay, I'm hoping everyone's okay with that concept. That's what we're looking for. Square roots of I. What times itself will give us I. All right, this one, I can't think of any off the top of my head, so it's time to get visual with it. Everyone give me a little complex plane. I would be right here. There's I. As I said, be visual with it. And again, I know it's going to seem silly because it just looks like it's I, but let's write that in all its comprehensive glory there. So I really is 0 plus 1I. And that's important because now that gives us a fighting chance in terms of finding R and finding theta. So guys, you know how to pull this off. R is just 0 squared and 1 squared. Everybody do that. And I believe you just get 1. And I'm trying to keep these easy for you, and I'll continue to do that. But it does look like R is 1. Theta is an interesting one right here. I get inverse tangent of 1 over 0. I am curious if you spot some issues here, everybody. Am I going to be able to do this on the calculator? Should I even bother on the calculator? No, because I can't divide by 0. So I have a tangent ratio that's undefined. So let's go to our little visual cue right over here. What is that angle from here to here, everybody? Well, I see it as 90 degrees. So there are a couple spots where tangent is undefined, either 90 or 270. If we were down here, obviously it would be 270, but we're up here, so it's 90. So our complex number, the number I, again, as odd as it sounds there, is really 1 cosine 90 degrees, I sine 90 degrees. That is the number I. Okay. So now what we're going to do is manipulate that complex number in polar form. Everybody, change R, change theta. And here is how the changes are applied. We take the principal root of R. In this case, since we're talking square roots, we're going to take the square root of R, the principal square root of 1. And by the way, square root of 1 is 1. Nice and easy there. And then what we're going to do is change our theta. So our original theta is 90 degrees. We need to include the 360K to get it moving along from angle to angle. But we're going to take 90 and divide it by 2. Square roots, so n is 2. Okay, and then I sine. Same deal, everyone. Starting with 90, using the 360k to get all our answers, but really it's a 90 over 2 situation. All right. I might have enough room down here, so I think I'll run with it. And guys, you can start at any number. As I said, my opinion is that the easiest thing to do is let k be 0 first. That's how you're going to start your cycle. And let's see what happens. So square root of 1, everybody, happens to be 1. Okay, and that's kind of nice. And then I get cosine. Now let it take over, everybody. What this just means right here is you're going to let k be 0. Easy to do, because 0 times 360 is just 0. So this is 0. Add the 90, so I'm just 90 on top, and 90 divided by 2 happens to be 45 degrees. And obviously, same thing over there. Put a little equals, and by the way, everyone, this is one of your answers. If I square this, I'm going to get I. Now the next one, same deal. Keep your new r, which just happens to be 1. And again, you get better and better at this. You can start to see the change. And this is sort of where the change occurs. This is where the 360 comes into play. 360 divided by 2, everybody, is just 180. So as a matter of fact, that's what we're going to go up by, 180. But just if I didn't know that, I would put 1 in for k. So 1 times 360 is 360, plus 90 is 450. So the top is 450, and I divide by 2. 450 divided by 2 happens to be 225. And that, everybody, happens to be your other answer. If I take that number and square it, I get I. Now, if there were more, again, theoretically, what we would do is just add another 180, add another 180, add another 180, etc., etc. It just so happens if I add 180 to this right here, it looks like I would end up getting 405, if I'm seeing that right, which, as a matter of fact, is the same position as this. So our numbers, even if I just kept going, now don't do this on your paper, but if I kind of dot this and kept going, I would just keep getting these same 2 answers over and over and over again, because there are an infinite number of angles that have these ratios, as we know. But regardless, just one last time on this, if you're wondering, okay, and if you don't want to put k in, here's what I would do. Cover up this, get 90 over 2, get your first one. Then whatever this divided by this is, that's what you go up by. So in this case, 360 divided by 2 is 180, so I go up by 180. On the last one, sorry, I just, again, thinking out loud with this stuff. In this case, 360 divided by 6 is 60, so you knew it just goes up by 60s. And you do it as long as you can until the cycle stops. Okay, hey, let's finish this up, everybody. Long lesson, I understand that, but let's close with a flourish. So I would distribute this in after getting my ratios here. So 1 times the cosine of 45 degrees. Cosine of 45 is root 2 over 2. Plus I, and times root 2 over 2. Here's one of your answers. If I was to take this number and square it, I get I. This one down here, cosine of 225 is negative root 2 over 2. And then minus, here's my I. Should have put it on the back, but that's all right. Sine of 225 is negative root 2 over 2. And guys, there are your 2 answers. 2 square roots of I. 3 cube roots of I. 4 fourth roots of I. You get the picture. All right, I told you this one's a great, tough lesson there. So take your time with it. Breathe deep. Try some, and let me know if you have questions. Thanks, obviously, for taking really good notes here. I hope it'll pay off as you learn this material.